Okay, so hello everyone, welcome to our this week Rutgers Efficient AI seminar. And today we are very glad to have Professor Haitong Li from the Purdue University to give us this talk about the in-memory computing for the emerging AI workload. And Professor Li is currently assistant professor in the School of ECE at Purdue University, and he got his PhD and master from Stanford, advised by Professor Philip Wang. And his research interests are in the new memory device technology, circuit design, and 3D integration for energy efficient computing towards machine learning. And that is a very emerging research area. And Professor Li has published over 60 papers across the different technical stacks and like in many prestigious scientific journals and conferences, like the Natural Electronics, IEDM, VSI, SSCC, ISCA, DAC, JSCC, and so on, with over 3,900 citations. And his work was particularly featured as part of the new computer trajectory for energy efficient computing in the SRC roadmap and the decadal plan for semiconductors. And he was invited as a participant in the 2025 Japan American Frontiers of the Engineering Symposium, organized by the U.S. National Academy of the Engineering. So now let's welcome Professor Li to give us this talk. Haitong, it's your turn.
Thank you so much, Professor Yuan, for inviting me. So in fact, I followed some of the past seminar talks. I find those very useful, and it's really my honor to get online and join you folks to share my own research. Hopefully, have more follow-up discussions. So I will be briefly talking about some of our recent works and also the past efforts and ongoing explorations into how we can make transformers and some of these beyond transformer models run more efficiently at the edge. And the particular approach that we are taking is what we call compute in memory. So essentially, think of this as you go from the home to work, right? So you are basically suffering this traffic in between. And what we want to do is essentially kind of like work from home. So you have computations happening directly where the data reside, and this is the direction we are pushing. And in today's talk, I will be talking about approach where we call this heterogeneous in-memory compute, right? So instead of just taking one particular memory technology to perform computations, what we find actually is you can have more efficient operations tied to some of these emerging workloads if you have heterogeneous, right, devices in your memory systems. So as a high-level background, right, so I'm sure we all know that, today's AI workloads have a energy problem, right? So this is more, increasingly a issue when there is this isolated sort of development between devices, circuits, architectures, and systems. So in some way, the device engineers package the best of the transistors and turn them into a black box package. And then the system designer take them, but they still run into this power wall and memory wall issues that do not really fully exploit the full potential of these new nanoscale transistors and memory cells. So what I want to argue really is that we need to take these exciting but isolated advancements from devices to systems and embrace the co-design approaches, right, to meet the growing demands for the AI hardware. What we observed really is that memory has been leading the way to diverse AI hardware, right? Because they open up a bigger design space that you can play with to construct different domain-specific architectures to emphasize energy efficiency or programmability and different adaptation to different domains. And in that pursuit, we saw a lot of opportunities in what we call CMOS plus X. So the idea is to augment the silicon CMOS technology with back-of-the-line compatible new materials that can augment your logic and memory. And that you can think of this as added functionalities with better efficiency but all within the CMOS ecosystem. In my lab at Purdue ECE, particularly we focus on a few directions to pursue energy-efficient edge AI hardware. So first, part of today's talk, I will talk about how we bring machine learning computations inside heterogeneous memories, right? So remember, these are the memory technologies that go beyond single type, and they can leverage the strengths and characteristics of each other and combine the best of the two. We also are pursuing monolithic 3D integration, putting those memories on top of silicon CMOS, effectively forming these 3D memory cubes that are more efficient, higher density than the existing memory devices. We also are working a little bit on the EDA side, right? How do we take some of these CMOS plus X triplets into this larger scale 2.5D and 3D integrated systems? So along those experimental efforts that we're pursuing in parallel, we're also working on modeling and simulation, right? Building the framework for design explorations, and we welcome more users and collaborations. So to get started in the first topic, I want to talk about first the issues with today's computing memories, right? So a lot of efforts focus on taking the emerging embedded non-volatile memories to perform computations very efficiently at the edge. So really the promise of these emerging NVMs are that they don't really need power to retain data, right? So these are initially targeted at a replacement of embedded flash and other edge memories that are really low power to go along with your microprocessors. And then people realize that if I perform computations directly in or near those emerging NVMs, you can also get very high energy efficiency. But so far, there are two gaps in this domain, right? First, really is if you compare many of these edge computing in-memory accelerators, there is a large precision gap between the really the high performance processors, your ARM Cortex core, and even modern GPUs, even at the edge. You can often have very high precision computations done in those processors and processing NPUs and GPUs than what you can do at this inside this computing memory cores. So largely, a lot of the prior efforts focus on performing integer-based operations. The other gap really is the speed, right? So we are talking about gigahertz operations for those modern processors and NPUs, whereas many of these edge computing memory cores run at a much slower speed due to this inherent lower sensing speed of NVM and large latency associated with the ADC conversion, right? Particularly for the analog CEM approaches. To address the first bottleneck, right, the first gap coming from the precision perspective, right, we want to afford to have very high accuracy for inference workloads, right, particularly for some of these challenging models like transformers. So really, you need to go from integer precisions really towards floating point operations, even for the inference. So the challenges for designing floating point computing memory design really first is you need pretty considerate overhead to convert between integer and floating point. Naturally, right, some of these NVM micros are easier to design for integer storage and accumulation. But then you have to convert the accumulated result in the integer domain or precision domain data format to a floating point data format, right? That's the first overhead. So that is not only taking up silicon area, but also the cost of energy and latency. The second challenge really is you have to do the so-called pre-alignment, right? So this is needed to take your Mantissa input, feed into your NVM compute cores, right? These are the memory arrays performing the vector matrix multiply before you perform accumulation, right? So this large shifters to perform this pre-alignment just to handle the floating point data format. That's a decent overhead that we want to get rid of. The third, really the bottleneck and challenge is during that pre-alignment, you will introduce these additional overhead bits, right, these padding bits to be able to align and then perform the floating point computation with both your mantissa and exponent components. So there is going to be some loss in the computation accuracy just inherent to this pre-alignment process, right? So they do not only introduce energy and area overhead, but also introduce precision loss that you cannot easily recover from the algorithm side. So taking all these challenges into account, the first, our solutions is to really leverage the heterogeneous memories, in particular, RRAM, being one of these more mature NVM technologies being developed in the foundry, and Gensel embedded DRAM, right? So this eDRAM are CMOS logic compatible, right? They use exactly the same logic process. They are much denser than SRAM because they use a few transistors. And they really just need to have the refresh operation, right? That's the cost of having eDRAM compared to the SRAM. But once you take these two memory components together, we find that if you map your mantissa and exponent from your floating point data format in RRAM and eDRAM, right, separately, and then have a fusion micro to perform computing memory, so that significantly reduce the overhead of the area required in the traditional, FPCM design, right? So this is largely because that you can get rid of this pre-alignment logic and from the shifters, right, to moving them to the embedded DRAM itself. That do not only store the exponent component, but also perform computations directly, right? Taking the mantissa from RRAM. The second benefit then is because we get rid of the pre-alignment and leveraging the combination of RRAM and eDRAM to do the data storage and compute together, we can save this potential accuracy loss, right? Get back this accuracy once you have this alignment-free computation done in this FPCM design. And I will talk about more details how that is achieved. But these are the high-level solutions, right? So we try to perform floating point computations, right, directly in memory. But instead of taking just one type of memory, whether it's SRAM or NVM, we try to combine the static charge-based memory, like the dynamic charge-based memory, like embedded DRAM, and static NVM, like RRAM, together to map this FP data format directly into them and perform computations afterwards. Remember the second challenge, right, the gap I talked about is the speed, right? So traditionally, the NVM technologies suffer from slower sensing speed, largely because they need to have long latency to stabilize the current during the readout. Because naturally, all these memories, whether it's RRAM or PCM or MRAM, they are resistance-based memories, right? So you are trying to sense out either resistance or the magnetic resistance from the memory cells. So that current-based sensing process is intrinsically slow. So in this work, we are trying to develop very fast voltage-based sensing, right? So the voltage-based sensing is not new. We know that we can convert, into the voltage domain and try to sense the voltage change. So we have been developing high-speed voltage-based sensing amplifiers that really allow us to enable very fast sensing. And that can be read out directly before the is stabilized, right? So that again, additional latency benefit to push the frequency even higher. So at the high level, right? So the benefit of combining the NVM in general, right, in this work, RRAM, with the CMOS memory like SRAM or eDRAM, is that you can optimize your system, right, in different multiple dimensions, right? In this work, the energy efficiency, right, measured by the number of operations per watt, is pushed higher than the state-of-art eDRAM and SRAM design, and particularly the NVM-based designs, because we map the floating point data format more efficiently and get rid of many of these overheads, such as pre-alignment, that is taking a lot of area and energy. And at the same time, right, so we kind of push the operating frequency higher and closer to what this modern processor and some of this edge GPU can offer. Of course, we are not there yet, because we have done some of our prototypes in the more legacy nodes. But this approach is promising because you can push forward and really close the gap between this edge AI hardware versus what some of these generic general purpose processing units can do. All right, to get into the details of this RRAM-eDRAM CM design, so this is providing this more schematic view of what's really happening. So essentially, we have two types of memory arrays, right? So RRAM responsible for the Mantissa bit storage and as well as the model weight storage, right? And then for the embedded DRAM, it is storing the exponents, right? And this sort of heterogeneous memory really break up your FP by design. And in the beginning, right, so these shift vectors will be first written into the eDRAM macro, right? So this is where we get rid of this pre-alignment by making this FP vector multiply essentially, sort of like a shift operation. And then input Mantissa bits will be injected in bit sequence, and then row by row, these input vectors will be put into your eDRAM, and this is where the computation happens. Because the eDRAM is, by design, unlimited endurance, right? So we do not need to worry about the write operations. Whereas in the pure NVM designs, you really have to worry about how many write operations you have incurred over the lifetime to prevent RRAM from being wear out, right? This endurance limitation. So then the result is going to be accumulated, right? So these are, the partial sums. Maybe I can use the pointers here, right? So these partial spatial sums are going to be accumulated in this accumulator, right? So these are the digital logic designs at the edge of our eDRAM arrays. And this output results will be temporarily accumulated, and then sort of to do the final overflow check and pack the to be a complete data floating point result, right? So essentially, the RRAM-eDRAM handles storage and computation, whereas the digital logic peripheral at the end will handle the final sort of overflow and packing for the real floating point results. Right, so at the end of the day, right, so this is one example. We use this simpler FP5 to illustrate, right? So essentially, we unpack the original floating point data format, and then perform the computations, right, in what we call 3D MAC. And then that is read out after embedded DRAM. All right, so this is the top architecture that we prototype our ideas of integrating RRAM and eDRAM. We call this chip Centaur. So essentially, we have bunch of RRAM macros. So this was in collaboration with TSMC. So we use foundry RRAM cells and design our own analog macros, right, for surrounding the RRAM. And then once they are wrapped into a larger Mantissa CM macro, they are integrated with our own customized Gencell eDRAM macro together with what we call a CM bridge, right? This bridge is a very simple macro to macro interconnect that facilitate the movement of the Mantissa to this eDRAM exponent array. And then surrounding those, what we talk about, so the accumulator that handles the partial sum and overflow check. And finally, they are interfaced with global SRAM buffers and a top controller that handles the actual workload mapping and handles instructions for computations. So the other use case of RRAM, right? So not very obvious here is that we also leverage the non-volatility of RRAM to store the exponent and signs, right? So these are to make sure that you have a persistent on-chip storage for those bits. So basically, the flow mimics what we talked about earlier, right? So having this exponent and Mantissa performed in RRAM and eDRAM, and then the partial sums get accumulated in these 3D MAC accumulator, and then these are finally checked with overflow and subtraction to get a final output. We prototype this chip in 40 nanometer process. in TSMC foundry process, and we mapped a customized tiny vision transformer model with model weights stored in RRAM, and this is a testing setup. So you can see that we essentially get a tiny VIT model and then interfaced with FPGA control, and then the model is entirely mapped onto this edge AI chip. So this is the measurement results. So we managed to push the frequency in this particular prototype into up to 600 megahertz, the nominal VDD voltage, right? This is almost bounded by the technology limitation because we were prototyping a 40 nanometer technology node, right? Pretty old node. So you see in this waveform, right? So we measure the end-to-end latency on the order of roughly 11 or 12 microsecond, right? So from the start of breaking down your floating point data format, right, storing in the RRAM and eDRAM, towards end where you have the final FP, complete FP output readout from the peripherals. You can imagine that every cycle of the floating point computation, this is roughly the latency it takes. In terms of the breakdown, right? So some of these observations. First, this is we call this a digital computing memory because even though we have analog designs around RRAM and eDRAM, the final accumulation and post-processing happens largely in the digital logic. So that is taking up roughly 70% of the total power. What this means is ideally, if you scale this design from 40, right, 40 nanometer technology node to more advanced nodes, this design will benefit more from the technology scaling itself, right? Because largely all of this digital logic can benefit from the lower power and from a advanced node. Whereas the RRAM and eDRAM macros themselves do not really consume that much of the power, right? So they are by design very efficient to handle the FP computation. Area breakdown wise, eDRAM and RRAM occupy roughly similar area. So this makes eDRAM pretty attractive, right, as an alternative to pure SRAM based design, right? Because SRAM, at least you need 6 transistors or even more. Whereas for the eDRAM in this design, we use a 3T GaN cell. So it's a smaller and more compact design. RRAM benefits from inherently smaller sort of feature size, but because we are putting RRAM onto 40 nanometer CMOS process, so it's really limited by the transistor, not RRAM devices themselves. So we also benchmark the performance of the model inference and also the figure of merit taking energy efficiency, speed, and inference quality. So on the left, you see this accuracy curve, right? This is where we sweep the frequency and try to measure end-to-end accuracy running our tiny VIT inference workload on CFR10 dataset, right? So it's a small workload mapped onto the chip. But compared to the baseline software accuracy, right? So gained from just running from a baseline GPU in the data center, we are really close, right? Almost just 1.7% drop in the accuracy from the direct hardware measurement. So this is purely thanks to the execution of the floating point computations, right? FP8 data format that retains the precision of the work of the model itself when they are mapped into this emerging AI hardware. And so this is one of the advantage of the digital computing memory compared to pure analog approaches, where we don't really have to worry too much about signal to noise ratio and some of these variations. In terms of the figure of merit, right? So we benchmark over some of these previous works. So because we can operate faster, and retain the results better with very decent energy efficiency. So we outperform some of the state-of-art accelerators in both NVM and SRAM designs by a large margin. So finally, I'm going to show this chip specs, right? So this is, again, done in 40 nanometer process with foundry RRAM cells. So we put roughly 800 kilobit of RRAM with 256 kilobit of eDRAM, both serving as storage and compute, with a small SRAM buffer operated at most 600 megahertz frequency. and they support FPA data format by design for both input activations and weights. So this is a key to retaining the inference accuracy. So only 1.7% loss from this ideal software baseline running the tiny VIT model. And we achieved around 38 teraflops per second per watt energy efficiency, a measure at the peak performance. So moving to the next, I want to talk about what's next, right? So we observed that there is tremendous opportunity of taking heterogeneous memory technologies and leveraging the power of computing memory, right, to make some of these edge machine learning workloads more efficient and also robust and reliable. But also we have to recognize that there's a limitation, right? You see that we were only able to fit a tiny VIT model, right, an edge transformer on chip because of the limited hardware resources, right? This may be fine for the edge applications, and it's also an important domain. But if you want to take this from a tiny ML edge to something larger, let's say you are operating with a larger privacy preserving workload that you really need more compute power, but you cannot afford going to the data center, right? You are kind of in the middle, but you want to stay at the edge. So this brings us to the next idea, which is the CMOS plus X chiplets, right? So you can leverage the advancements of heterogeneous integration, right, and not be bounded by the limitation of a single die. So this is the direction that also we are working heavily. So this is open source framework that we developed last year to help both architects and technologists, right, to think about how do we harness these heterogeneous CM technologies, right, in both 2.5D configuration, right? Think of your HBM along with your CPUs, GPUs, and accelerators, as well as more advanced 3D configuration, right? Think of those as the 3D stacked ICs, right? So where you can stack both your memories and logic in multiple vertical layers. So we developed this design exploration framework, taking the information of your workload, such as what kind of transformer and other neural network topologies you have, and then understand the technology configurations. For example, how you configure your 2.5D and 3D stacks, what kind of interconnects you were using for constructing the networks on chip and on package, and building models for the memories themselves, right? So that first initially take RRAM and eDRAM as an example, but this can be extended to arbitrary NVMs and silicon CMOS memories. And then we constructed sort of the energy, latency, and area models that allow you to peek into different kind of design knobs and design options, right? For example, you can choose to mix and match different kinds of memories in either same or different technology nodes, right? So that's one of the convenience of features of chiplets, right? You don't have to be stick around the same technology node, right? You can mix advanced nodes versus more cost-effective nodes, such as the 14 nanometer we talked about. And then because of the involvement of diverse memory technologies, we are not bounded by their reliability limitations, right? For example, many of these embedded DRAM macros might suffer from frequent refresh, whereas many of these NVM macros might suffer from endurance, right? So by mixing them together in a system, you can then have a reliability-aware mapping from the model to the hardware themselves, right? To map the right portion of your models and right operations to be aware of their corresponding endurance or retention requirements of the technology themselves. So that overall gave you a more efficient but also more reliable system mapping. So this is some of this example mapping, right? So for example, if you take a transformer or maybe a larger transformer beyond what we discussed in the Centaur chip, right? You may have to map both static and dynamic type of matrix vector multiply. For example, in the attention head, you have more of these dynamic operations, right? The QQ vectors are continuously updating, and you cannot afford to have a stationary data flow and leverage NVM heavily, because that will very fast wear out your memories, and you get very quick drop in the accuracy and a bad device. Whereas for many of the static matrix vector multiply, you may be okay to have this traditional way to stationary data flow and leverage this extreme energy efficiency gained by mapping them into NVM, right? So this is one example. Beyond inference, we also support continuous learning, right? So in many of these adapter-based models, people insert these very lightweight adapter layers, right, in between your attention kernels and projection and fully connected layers that need to be trained, but very lightweight. And those see more weight updates than the other layers during the continuous learning, right, seen with different tasks, right? For example, you may be switching from one particular scenario to a different task, then you need to kind of fine-tune your model, right? But these adapter layers enable this continuously, and that is heavily relying on some of these CMOS type of memories like embedded DRAM, right? So that are more efficient, and you don't really need to retain these intermediate results all the time, right? So they can be more friendly to this eDRAM, even though they sometimes need refresh. One example that our framework support is, again, that a combination of NVM and charge-based memory, like embedded DRAM, that are denser and more efficient than SRAM, right? So here, both inference and continuous learning, you can leverage different configuration of these chiplets, right, in different technology nodes to give you the right combination of CEM macros to lead to the best efficiency, taking into account both the energy latency cost on die as well as the energy cost of data movement, right? At the end of the day, once you go from single chip to multi-chip, you are paying for the overhead of the network on chip and network on package, right? So that is dependent largely on the technology fabrics you are using too, right? So in the 2.5D, what kind of interconnects vertically and horizontally you are using, and in the 3D, both, right, will impact the overall landscape of the energy versus latency versus area. So this is one example, right, I want to show how the interplay between the NOC and NOP versus these heterogeneous CEM macros can come into play. So if we sweep the ratio of the RRAM and eDRAM capacities, right, in the entire system, so that will lead to different sweet spots, right? So given the cost and overhead of this communication, so there will be somewhere where the communication cost will be minimized such that you can achieve the overall best EDP given different ratio or composition of these heterogeneous memories, right? So they are not optimized standalone. So the key message here is really you have to balance everything together. And also going from 2D to 2.5D and 3D, one of the key benefit is that you can have really this, I would call this edge large language model, right? They are not data center scale, but it's beyond these tiny transformer models. And you can gain tremendous benefits in terms of energy efficiency and EDP also for the workload level going to the 2.5D and 3D. Of course, the caveat here is not all the models behave the same, right? For example, some of these models, due to their autoregressive nature, they may not see much of the benefit. One example is, this GPT-2, right? So you don't really gain too much of the benefit going from 2D to 3D. But some of the other models, they may see a higher boost and in different situations between inference versus fine-tuning versus continuous learning, right? So these are just examples I want to talk about, but you are welcome to explore the framework, right, to see how that may benefit your own research. All right, so the last portion of the talk, I want to dive into a little bit different topic. Transformer is great, right? But it's not everything, right? So we know there's limitations, especially when it comes to advanced reasoning and some of these applications that tend to mimic what humans do better than some of these large language models, right? So this is where we are actively working on in the domain of neurosymbolic AI, where we want to combine this fast learning and feature extraction capability of neural networks together with this more robust reasoning capability of some of the symbolic models. I will give one example of that symbolic component, but some of these famous, models in the past already are partially using this kind of semantic, right? So, for example, in the GPT models, you already have these word tokens, and that represents some of the symbolic information. The AlphaGo, right? You have this Monte Carlo tree search really as one of the symbolic techniques, right, to evaluate game positions. So it's kind of gaining momentum and has been probably more promising in some of these more cognitive applications than the pure language tasks. And really, the idea is to combine the best of two, right? So combine the feature learning capability of neural networks, maybe transformers even as backbones, but also leveraging this emerging hyperdimensional computing, right, as the symbolic technique to project information into a white box and facilitate this more deliberate sort of vector-based reasoning tasks, right, in this second backend. What our lab is working on in this direction is to provide, really the future hardware fabrics, right? Because many of these neurosymbolic workloads and models are becoming very heterogeneous by nature. They are even more complicated than what you find in the transformers, right? Not only bunch of different attention heads and projection layers, but even more, right? You now have a front end and back end, and you need to coordinate the execution and make the computation flow more efficient, supported by the underlying hardware. So what we are pushing for is to expose the unique characteristics of the CMOS plus X, right, to be able to support these kind of new use cases. And in particular, really the opportunity here is the plus X, right? We gave examples of RRAM that really allow us to specialize, whereas the CMOS layer provides this power of abstraction and scaling, right? Especially if you go rely on the digital logic in some of these components. So the CMOS plus X together really provide us with tremendous opportunities. And this is a larger landscape than what I talked about in the first half of the talk, right? So beyond NVM, you also have other emerging devices that are all compatible with silicon CMOS in the backend line, right? For example, you could have this very low leakage, high performance new transistors, right? Using new materials such as oxide semiconductors and two-dimensional materials stacking on top of silicon CMOS, right, to build logic kernels and memory macros. You can also have a diverse set of NVM, right, beyond RRAM, right, in maybe taking advantage of other features that those memories offer to construct efficient compute kernels in those neurosymbolic models. So these are some of these really old works that we have done in the past that take some of these examples and map them into emerging devices. So earlier we have worked on trying to look at hyperdimensional computing and address their core arithmetic operations, right? Arithmetic kernels, which are multiply, accumulate, and permute. And we realize that it can be very efficient if we perform this kind of map operations directly in a 3D vertical memory. So leveraging the 3D connectivity and this vertical pillar structure to perform multiply and then accumulate, and then the shift operation can be done efficiently, right, to emulate the permutation in memory directly. So all these three operations do not need to go outside of the memory array. And later we have taken this associative memory sort of designs, right, integrating CMOS and RRAM to address the operation of memory augmented neural network, right? So that is one sort of example of how you can augment your neural network with something else, right? So to give a little bit of background on the hyperdimensional computing, right, as a core backend in this neurosymbolic workload or models. So essentially, this is a very lightweight sort of computing framework that project information into high dimensional space, right? Think of translating my floating point numbers that I talked about earlier into very long binary vectors, right? So, and they are very long, such that in the orders of kilobits scale, right, in terms of the width, so that you don't really need to worry about they are colliding to each other in the high-dimensional space, right? So they are by design nearly orthogonal to each other, representing different kinds of features and information. And then you take this core, multiply, accumulate, and map of permute operation, or what we call map, to build richer and more hierarchical informations and representations. So you can think of this process almost as a compression, right? From information theory perspective, right? They are compressed into this same length vector, but with richer information contained in this single vector, right? And they have this HD computing framework has been very successful in different domains of applications, right? From semantics, language tasks to handling these analog biosignals, right? To do some of this initial reasoning and control that are more promising if you think about them in the context of neurosymbolic AI. So under the hood, right? So these are the map kernels I keep talking about. Multiply, it's very simple, right? You take two kernels, two vectors in the bipolar or binary domain. This is essentially an XOR operation. Accumulate, you are essentially accumulating a number of ones across a number of vectors you have when you are doing this encoding and compression. And finally, you need to have a permute to preserve this orthogonality between different final vectors, right? So these are all the core arithmetic operations. They can all be mapped efficiently once you start with generating these vectors, right? So this is a key of performing this HD computations in memory, which is you need to have very efficient random number generation technique itself. So earlier we have found that if you take many of these emerging memory, with RRAM being one example, you can translate intrinsic device physics into these orthogonal HD vectors in situ, right? This, zero and ones, right? They are generated just by having a very weak programming pulse on these RRAM devices, right? So then by leveraging the intrinsic stochasticity of the RRAM, you then end up having a bunch of 0 and 1 in your memory macro, and you can even tune the randomness and engineer the sparsity of these HD vectors by physics, right? So this is done directly at the device level. Once you have these vectors, they don't need to go out, right? So this is the key. You don't want to pay for this data transfer anymore. So the execution of the map is directly done in memory. So this is the earlier example I talked about, right? So performing this map operations in a 3D vertical RRAM array that can map all these three kernels very efficiently without leaving the memory themselves. You may wonder why we are doing this, right? So with this emerging memory. So one key reason is many of these HD models have amazing tolerance to the hardware errors, right? So this is one example, probably not relevant anymore, right? Nobody does this language classification with nearest neighbor, but still, with many of these traditional ML, you do see a very sensitive sort of behavior when you start to have a large portion of hard errors in your hardware. Whereas HD by design, because of this, holographic representation with very long binary vectors, they do tolerate with very high, tolerance, right, resilience to the errors in many of these memory cells, right? So that's one attractive factor for marrying the HD computing with these emerging devices. So as an extension, right? So then we think about how do we really augment this vector symbolic or vector-based operations, right? So we need to leverage the feature learning capability of neural networks. So this is earlier example where people were looking at this meta learning, right, with memory augmented neural networks to have an explicit memory side by side with your neural network. So this mimics what we want to do because we want to have these vector symbolic operations done in this kind of associative memory, but we lack of a good feature extractor, right, for pure HD paradigm. So combining a neural network with a vector symbolic component exactly match what we want to achieve exactly, right, at the end of the day, which is a more robust and efficient neural symbolic model. And taking that example, we do a new chip design, and which is leveraging RRAM, not for the matrix vector multiply, but really encoding the feature vectors and perform the similarity search, right? So traditionally, you may find similar products in your IP routers, right? So those are the microprocessor where you have some of this database search to look up your IP address. This is what we call content addressable memory, right? These are mature products in the microprocessors. But what we need now is something different, right? Because we don't want to look at exact content. There's no exact content, right? So all these feature vectors, they are projecting in this hyperdimensional space. So you have to track the similarity by performing the approximate match. So we encode the values into this 2T2R RRAM cells in the complementary fashion, and then search the similarity with this one-shot learning technique, right? So this is the Sapiens chip we have done a few years back that leverage integration of RRAM on top of silicon CMOS to perform this kind of approximate search and one-shot learning. And compared to the other designs, because of the nature of approximation and very high density kernels, right? Because this RRAM 2D2R cells are very compact compared to SRAM or other designs, we have a state-of-art density and search energy. And once you map these vector operations in memory, so you can actually perform this very robust because this is read intensive, so you don't really have to worry about endurance. So this is a read inference accuracy versus number of test images that we have, basically stressed the chip over millions of images, so they can perform this one-shot learning and inference very efficiently with this kind of memory augmented neural networks. All right, so to conclude my talk, in the future, right, so where we are heading really is to take all the learnings we have done so far in both hardware prototyping and some of these code designs. We want to, enter a stage where we can really combine these powerful neural networks, right? Maybe at the level or at the scale of large transformers, with this powerful representation technique in the HD space, right? So taking the vector symbolic architectures and HD computing framework as the backend to augment neural networks, right? So that you can have both faster learning and very robust reasoning in one heterogeneous model. And to do that, we really want to have a cross layer and co-design approach, right? So taking our learning so far, and this also calls for a new class of hardware beyond what we've seen so far, right? So you need to have robust support for these very complicated heterogeneous models. The data flow and the circuits have to be co-optimized such that there is no this limitation just coming from one layer or one side. So this is really the teamwork, right, from amazing team of students in my lab at Purdue, and a lot of this hardware prototyping work in collaboration with TSMC, proper research, and we thank funding from NSF. With that, really happy to share our research and open to discuss any questions.
I don't thank you so much, everyone, for talk and very, very informative. And I have several questions, but I would like to first ask the audience to ask. Yeah, so if you have any questions, so you can unmute yourself or you can input your questions in the chat box. I think maybe I can go first.
Sure.
Yeah. So I don't I think you have one slide shows the can you hear me?
Yes, I think you were cut off a little bit, but I can hear you now. But I cannot hear you now somehow. Will you?
Can you hear me right now?
Yes, now it works.
Yeah. I think you have one slide shows FEOL integration. Oh,
Sorry, you're asking the what integration? I didn't catch the question.
the FEOL. I think you have one slide show the FEOL integration.
Oh, I see. Let me go back to that slide. This one? Or maybe this one?
Yeah, this one. Yeah, so here, yeah, I think just the previous slides.
Okay.
Yeah, so here, right, for this one, so actually you don't need the BLL, so directly the FEOL, so it already can do this kind of the more high density integration, right?
So if you mean the silicon CMOS itself, right? So then you are saying you get rid of all the backline layers and without any of this NVM. So that will lead to the pure CMOS design.
Okay,
Right.
so
If you want to integrate any of these emerging memories and some of these logic transistors on top of CMOS, right? So then that's the backline I was talking about.
yeah. So here, so in this example, so all the devices you use here is the silicon, right? It's the CMOS, right?
So okay, so if you're referring to the Centaur chip, right? So this one, the SIM, because the eDRAM is in the CMOS, right? So all the logic, digital logic peripherals are in the CMOS. The RRAM are in the background line.
Oh, okay. Oh, RRAM is back. Okay, I got that. Okay.
Yeah. But then what's not shown in that chip is really the other components, right? So ultimately you may need other stuff, like if you have more complicated logic you need to build them, you may not want to go to the silicon CMOS, right? Rather you want to go into the background line and have new logic transistors to go along with your RRAM and other memories.
Okay, I got that. And I have another question. So, in many of the examples, actually, you integrated like the RRAM, like with the eDRAM, right, and SRAM. So I was wondering, so here, why you the motivation here, you kind of the mainly use the RRAM instead of other emerging memory, like the MRAM, FERAM, and so on.
So that's a good question, right? So let me go back to this figure, right? So I think all these different types of NVMs, they have their own trade-off for the use in the computing memory, right? Some of these may suffer from a smaller memory window. You have to design your sensing to be more careful, and that introduce some overhead. Some of this may be more robust, right, in read and write operations, and so you have different trade-off. So I think what we see when we combine these NVMs with CMOS memories, I think that introduce more benefits than picking a particular NVM cell or technology per se, right? So in the Centaur design, of course, you can get other memories. For example, you could have maybe MRAM or maybe PCM as a way for the Mantissa storage and the weight storage, right? So that I think that is not the core benefit, right? So the core benefit really comes from mapping the model, right, in an efficient way across both silicon CMOS memories and NVIDIA, right?
Okay.
But that may largely depend on the models you are looking at. So for example, in the transformer case, right, so we were mapping the Mantissa and exponent to the RRAM and eDRAM, but maybe in other models, you don't need a floating point, right? So maybe you are fine with integer. Or maybe some of this, for example, I was showing here in this modeling framework, right? So some of these models are seeing this both dynamic and static weight operations. So if you have a pure SRAM, that might be fine. But then you lose the benefit of having the static weight stationary data flow. But whereas for a pure NVM design, then you may suffer from endurance issue, right? Because your QPV vectors, they do need to have a continuous update. And that will drain your endurance very quickly, and that is not suitable with pure NVM designs.
So actually, that is also related to another question that for your, I think for your your simulation framework, your modeling framework, yeah.
Yeah.
Yeah. So here actually you can have kind of the different choices for the sorry. So here actually you can only use the RM, or whether you can also like to freely choose other emerging memory or
Yeah,
not.
we can capture different types of technologies, right? So that's really the idea. So you have a flexible design space at the technology level to combine different types of, SRAM, embedded DRAM, and NVM combinations, right, into this CM triplets.
Okay,
Um,
so that's good. So then here's my question. So in your design space, because we can have different level of the kind of the decision variables. Some is kind of the how to choose the memory type, right? And at the architecture level, so we can choose that a different type of the stationary data flows and so on and
right.
so on. I want to know that right now, in your framework, for the kind of different decision variables, whether you decouple the selections or you jointly kind of to determine that, in a kind of even bigger design space or not.
That's a good question, right? Right now, I would say we are not fully decoupled, right? Otherwise, it would be really large, vast design space. So it's the link between the technology level, right, the circuit level versus the mapping itself is partially driven by the reliability, right? So I'll give one example here. Right. So for example, right, so in between, for example, if you have inference versus continuous learning workload, right? So then based on that, you already know that many of these operations might be very endurance sensitive, right? So that you naturally would want to go to maybe EDRAM, right? Given different refresh or retention requirement. So even though the framework by design, you can have all of this mapped to RRAM, right? So get rid of any of these EDRAM CM engines. But that we know in advance that is not sort of a reliable mapping, right? So you kind of prune that space in advance, right? So I would say they are partially coupled, right? Not really fully decoupled. But if you have very different ways of optimizing given the same reliability sort of requirement, then that's possible, right? We have the flexibility of choosing different mapping schemes, right? For example, with different characteristics of EDRAM, your different designs, you may choose maybe different data flow, even when there is no endurance or retention problem.
Okay, so like here, some parameters of your NVM and the DRAM, so they can also be kind of freely to reallocate, for example, so like how many kind of the memory size should go for the emerging memory, how many should go for DRAM.
Yes, those are the design norms.
Okay, that's great. That's pretty comprehensive and flexible. Okay. And some questions from the audience?
Hi, hello, Professor. I do have one question.
Sure.
That is related to hyperdimensional computing.
Mm-hmm.
So I would like to know, like, what are the limitations of hyperdimensional computing? It can be based on different applications as well. Like it's not doing good compared to other learning algorithms. It can be, let's say, SNN or CNN.
That's a good question, right? So in my experience, many of these success that HD computing sees are, more of this, for example, 1D data, right? So representations, right? These biosignals, right? You can map the EEG, ECG signals, right? Naturally in the hyperdimensional vectors. In many of these cases where scenes are already pretty good, right? If extracting features, it may not make too much sense in trying to tweak your HD model, right, to compete. And this is really motivating us to really, chase for these neural symbolic models, right? Combining what neural networks are good at, right? Feature learning and very fast versus this, projecting information on maybe intermediate representations into HD space and do a lot of this reasoning and control stuff. that the CNs and transformer may not be as good or may take huge resources to do it. I think combining this probably is a better way to go than trying to tweak HD itself to be good at everything.
Okay. Another follow-up question, that is in software it is pretty much easier to define the dimension. Let's say large dimension I can do like 10K, 15K.
Yeah.
But when it goes to like hardware in terms that mapping in the memory or something, so it becomes a bit like complex for the hardware, right? So in that case, we can reduce the dimension, right? To or
Yeah, so if the question comes from efficiency perspective, yes, right. So there's a trade-off between how accurate or how robust your HD vectors are, right? With longer dimensions versus if you chase for efficiency, then you can trade off that by having a more compact representation, right? So, the smaller dimensions, shorter vectors. In terms of mapping, I think that's one advantage of HD, which is essentially when you construct all these map kernels, whether using digital logic or some of these in-memory compute techniques, the dimension almost is a tunable knob, right? For example, if you implement this multiply kernel in pure XOR gates, right? It's simply how long the chain is when you're doing bitwise XOR. Similar for the accumulate buffer, right? So I think that sort of make the design easier as long as you can fit all these HD vectors in hardware. But of course, right, the bigger space, the longer vectors, you're gonna pay for the dynamic and static power. You're gonna pay for area.
Got it. Last question about in-memory computing. So I have seen papers, mainly maximum papers implement like XOR, XNOR. Then I have seen half adder, full adder, or NOR and those kind of logic operation. But if we see the logic library, like people used for ASIC design or something, there are much more logic there. So is only doing XOR, XNOR is enough for in-memory computing? Or, I mean, what I'm trying to say is what's the future direction of in-memory computing? We can do, I see, few years. So like only few logical operations are there. So is it
That's
enough?
really a good question, right? So there is a gap, right, that is hidden here, which is for the many of these processors, they are more generic. So the programmability is really important, right? I would say in the future of all these CM designs, how do you go beyond single models, right? So the example of this neurosymbolic workload really, speak to that, because if you stick with a very perfect transformer accelerator, but then maybe a few years back, you have a better architecture or maybe different transformer models, then you lose the efficiency, right, of the ASIC. So it's more than just a few operations for sure, right? So in the past, largely people focus on building very efficient Macs, right? Because you have multiply, accumulate being the dominant operations in your scenes and all the other layers, even in transformers. And now you could have better attention kernels, right? And then next you could have better softmax units. But then if you lack the intrinsic programmability, maybe with on-chip instruction sets, then you can never compete with the versatility of the modern processors, right? So that's a hidden gap here. So one of the direction that we are working on that I didn't talk about today is how do we give that programmability to the computing memory chips themselves? So meaning that if I have arbitrary workloads, can I leverage what's on chip already to reconfigure and then program my chips, right, to make different models run also at the same efficiency or maybe similar efficiency. So pretty much blurring the boundary between a specialized CM core or chip versus a generic, maybe embedded processor or embedded CPU.
Okay, yeah, got it, Professor. Thank you for your information.
Other questions?
Oh, hi, Prof. I have a question.
Sure.
Okay, so I'll be considering more about the higher level because currently when you are building the, the heterogeneous company memory macros, so I understand you are like manually mapping the data flow of currently DNN workload to it. Yeah, so, but actually my question is in a higher level. So in the future, if the company memory comes into practical use, we will have a program model on it. So the my question is while different, like you are proposing a heterogeneous memory types for company memory. So how do you manage the program when different kinds of memories are sharing data? How do you manage the shared memory space between them? Or how do you manage the data's consistency and coherence between them? Because different memory have different reading latencies and writing latencies. So you cannot directly apply the memory model in CPU or GPU to it. So that's maybe not quite related, but that's a question I want to ask for a long time to a very authentic company memory research.
That's a really great question, right? So you are right. In our example, in many of other examples, the data flow is closely designed with what kind of memories you have versus their characteristics and what kind of roles they are playing, right? In our example, we have a particular break partitioning for the FP data format in between RRAM and embedded DRAM. So in that sense, we know exactly where we are playing with, right? The retention characteristics of eDRAM is known to us. The read and write energy and latency of RRAM is pretty known, right, in the design phase. So the entire chip is almost wrapped as just any of the ASICs you have. So I'm not an expert in programming model and compiler, but I would imagine that's going to be important, right? Regardless of whether you have one type of memory or two types or maybe more, then you have to handle how you map this arbitrary workloads, right? So that maintain efficiency but also being programmable. Just back to my earlier comment, right? So what we know working on is more on the instruction set architecture stage, right? And then if you interested in working on compiler and programming model, I think that would be promising, right? Definitely important. But what we want to provide for the community is something that people can really program, right? So and how do you write compilers for it? How do you execute? That is not really our expertise, and we'll welcome collaborations.
Okay, thank you so much.
Some other questions? Yeah, I just have kind of quick comments for the two questions just from the audience. I think they're quite relevant. So definitely, I think that those that the kind of system or the software level support for those that is for emerging memory is pretty important. And I know Haitong, you are working on those the ISA parts, and I think regarding the compiler, I remember there was some already existing work, right, for some groups that towards some maybe not quite comprehensive, but also working on some kind of the compiler for that, and also about regarding like the coherence or the data consistency. I think maybe right now, so for the application side, we don't need kind of that very kind of the comprehensive solution yet, because right now I think it's still come too long for us to consider to build a kind of the NVM based the GPU or CPU that kind of every kind of the general purpose accelerator hardware using the emerging memory, right? So right now I think the main focus is still on like at the edge side or so on. So in that case, actually, so the design space or that your compiler or need to be kind of the design is not very large. And in that case, I think Haitong, like just as you mentioned, that right now it's kind of the hybrid or the more manual selections that I think is already kind of the good enough, right? Because we don't need to over design for that. Yeah. So that is just some of my thought about that. Yeah. But in the future, like if you want to use those the emerging memory for kind of the more data center scaled applications, and then I think those are the like the cache coherence and all many kind of the architecture level kind of the solutions that is very desired. Yeah.
Makes sense.
Okay. Okay. So any other questions? So if no more questions, so let's thank our speaker again. So Haitong,
Thank you,
very
Professor Yuan, for inviting me. Really enjoyed the discussions, and thanks for everyone for joining the talk.
Yeah. Okay. Okay, thank you so much. Also, thank everyone to attend our this week seminar talk, and our next talk will be the 2 weeks later. Okay, thank you, everyone.
Thank you.
Thank you, Haitong.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye.